Thank you very much for waiting. It is now the time to start. So we would like to start the press briefing and actual machine on-site tour of Fujitsu and RIKEN's world-leading 256-qubit superconducting quantum computer. Thank you very much for attending despite your busy schedule. I would now like to explain today's procedures. At first, there will be a presentation regarding the world-leading 256-qubit superconducting computer from both institutions. Next, we will have a photo session followed by after the photo session, the Executive Vice President Kawasaki from RIKEN will be leaving due to prior engagement, and we will have a Q&A session for about 25 minutes. We scheduled to end this session at 11:30 a.m. Japan time, and we will have the actual machine on-site tour. For the lab room where the actual machine on-site tour will be conducted, we ask you to take the bus to transport yourselves. I'd like to introduce today's attendees. Masashi Kawasaki, Executive Vice President of RIKEN. Corporate Executive Officer, Corporate Vice President, CTO, in charge of System Platform of Fujitsu Limited, Mr. Vivek Mahajan. Yasunobu Nakamura, Director of RIKEN Center for Quantum Computing of RIKEN. Shintaro Sato, Fellow, Senior Vice President, Head of Quantum Laboratory Fujitsu Research of Fujitsu Limited. Wahara, the Head of IR Fujitsu Limited, will serve as the MC today.
Next, Fujitsu Senior Executive Vice President, CTO, CPO, and Co-Head of System Platform, Vivek Mahajan, please. Good morning. I am Mahajan, Head of the Technology at Fujitsu as CTO. As was mentioned by Mr. Kawasaki, I'm sorry, we have been conducting co-research with RIKEN. And so from myself, I would like to talk to you about the overall strategy of Fujitsu with regards to quantum computing. So Fujitsu has several key technology that we are focusing on. So looking at the big picture, first, of course, AI. We are promoting Kozuchi as AI platform, but not just AI software, but there are a range of technology that supports such software. This includes quantum computing and network, data and security, and conversion technology. When it comes to AI, all of these technology are essential for its evolution and even its existence. And as Fujitsu, we would like to promote Made in Japan. Of course, Fujitsu processor is Fujitsu Monaka. The 2 nano will be launched next year. And then there is the quantum computing. We're working with RIKEN. And we have been building the technology together. So as Fujitsu, we have this wide set of technology, but today I would like to focus on the quantum computing. So of course, the 256 qubit superconducting quantum computer will be the main topic for today. But this is one of the milestones within this big picture, within this big roadmap. Last month on the 31st, we launched the chip, the quantum computing chip. And then the next step will be the 1000 qubits. And near fault tolerant quantum computation is what we like to achieve. And ultimately completely fault-tolerant quantum computation. And this requires various technology to be channeled. There is the superconducting, but also last month in the quantum computing event, we talked about the high-fidelity diamond spin method. And together with the Osaka University, we're working on the star architecture. This is more on the software side. And quantum computing plus quantum supercomputing and quantum combination. Not everything is going to be quantum. So we will be promoting the combination of both. And we would like to lead this technology from Japan at the cutting edge of the world. So as mentioned, the 2056 qubit superconductive technology, we will like to guide you through the actual quantum computer later on. But of course, the next will be the 1000 qubits, and ultimately beyond the 1024 qubit. So we use this word beyond a lot. Near fault tolerant quantum computing. If star architecture can be realized, then the 60,000 qubit is theoretically possible. It's a hypothetical, but we believe that it is possible. So we are working with RIKEN to develop this technology together. And we would like to ask for your continued interest and your understanding that this is one of the steps within this big roadmap and strategy. So let me walk you through this Fujitsu's quantum computer roadmap. So we're at 2025. The 2056 qubit computer is being released. And then next year, we set this very aggressive target, the 1024 qubit quantum computer release. So not just the chip, but the control and the other various technology, including the refrigerator technology. Of course, the chip itself is very challenging, but in addition to that, you need the control electronics, which is another big challenge. And the refrigerator, again, the very big scale refrigerator that will be required needs a lot of technological development as well. So to be the world leader, we are setting this very lofty target together with RIKEN. And the near fault-tolerant computer, the early ones will be released in the near future. So that's where we are targeting. So thank you so much for your attention today. That is it for me.
Lastly, we would like to invite Head of Quantum Laboratory, a fellow SVP from Fujitsu Limited Fujitsu Research Center, Mr. Shintaro Sato. Good morning, everyone. My name is Sato. From my side, I would like to explain the 256 qubit superconducting quantum computer. But before I go into the actual explanation, I would like to explain Fujitsu's strategy for quantum computing briefly. As shown here, cover all the technology layers from the fundamental software application with the world's leading research institutions, because it is hard to do with alone by ourselves. And one of the strongest partner is RIKEN for us. This quantum computing requires a lot of hardware technology. So for us, we don't know where the end picture is going to be, but we would like to focus on the software technology that is not dependent onto hardware. That's one pillar. And for the hardware methodologies, we would like to think it in a broad perspective. However, there's a limitation of resource. But with RIKEN, we will be working on the quantum application, and we will be working on the diamond spin qubit with TU Delft. So currently, hybrid quantum platform is used, and conducting the research with our partners to develop the actual machine. But even before that, using RHCP technology. We have been working on the application development with our customers. And of course, today, I would like to explain the research and development with RIKEN. As Dr. Nakamura explained previously, our collaborative research with RIKEN started from 2020 and April 2021. As explained from before, we have established the RIKEN RQC Fujitsu Collaboration Center, and we have been working on the development of the superconducting quantum computer. The mission of this center is to develop key technologies to realize quantum computing. And we would like to develop hardware and software technologies to realize a quantum computer with 1,000 qubits and to develop applications using a prototype quantum computer, which will also get the end users involved. And we have been working on this collaboration research. And in December, 2020, October 2023, we have developed a 64 qubit quantum computer and also the platform. And this March, the 256 qubit quantum actual machine development was our target, and we were able to achieve that and be able to make this announcement. And the first phase of this collaboration center ended at the end of March, and from April, we have started the second phase, and we'd like to continue the basic technology development related to quantum computing further. And now development of 256 qubit system from the establishment of the center. This was our target, but there were challenges. The 64 qubit was developed at RIKEN and on our side as well. And we have visibility on how we should develop it. However, at that point, the size of the refrigerator or the performance, what we can use, the maximum was that what was used for 64 qubit with the same size of the refrigerator and a capacity, are we able to actually contain more than 64 qubits? And actually, can we cool it down? Was the challenge. As Dr. Nakamura mentioned, we did have the scalable design of the chip, and that was fine. But can we actually put everything in? This size limited refrigerator was the challenge. So we simulated the heat performance. Actually, refrigerators have multi-layers, and at each layer, they will calculate the heat balance. And they calculate if we put all this in, it can actually cool it down. So what we found out is the 4K stage is the danger zone, meaning the cooling capability. And this is the amplifier of the semiconductor, and that actually emits a lot of heat. So we have started from the selection of the amplifier, and the heat will emit it, and we need to release that in an efficient way. And it has here the housing design. So the housing design, and we thought of the thickness of the plate. And if we're able to design it well, we found out that even at the 4K stage, that we will be able to sufficiently cool it down. This is one of the good discoveries we had. And furthermore, the package is something where the chips will be stored. There were challenges here as well. Simply speaking, the number of chips will be 4 times, and then the number of wirings or the volume of the wirings will increase. So that the package that will attach to the quantum computer, that package will be large, but there is a limitation to the capacity of the refrigerator as well. So we need to make it smaller. So we actually adopted a small connect parts. So there were 4 times more of chips, but the bottom plate where the wires are connected, we tried to minimize it as much as possible. And as a result of that, we were able to store it inside the refrigerator. In addition to that, we will be looking at it later, but we have many components. So whether we are able to actually assemble this and can we actually repair it when it breaks down, we carefully designed it. And finally, we collected all the components and we had the visibility that we can cool everything down. And this does not end the story. Actually, there was one more challenge, 256 qubits. This is quadrupling. And then there will be a qubit variability. What that means is that, as Dr. Nakamura said, is that, as I explained about the smallest element and the Josephson junction, so that's the smallest limit, and it's a very thin. And the oxidation, the state of that, and that is going to impact the properties of the qubits. And if we measure the resistance, we'll be able to see the variability. And there was about 4%. And when we developed the quantum computing, then the frequency of the quantum did not stabilize and the performance went down. So at the 64 qubit time, we have been involved in development, and we have developed the laser irradiation. And with the laser, by projecting it, we will be slightly oxidize the chip. And as a result of that, and we're able to have the variability percentage lower than 1% down to 0.6. Without this, even though we create the chips, the frequency will vary and we will not be able to use it. And furthermore, the process time is important. If you just leave the chip, then the properties will change because we are using the oxidation laser. So we have to store it as soon as possible. So this is compared to our company with it took 36 hours, but we were able to shorten it to 12. And then for 1,000 qubits, we are trying to shorten the time more. But we have been steadily working on such development. And also, you'll see this like this chart. What is this drop? You may notice this, but there are 3 quantum bits died. So the yield is 99%, is what this means, but there's still room for improvement. But when we compared to when we developed 64 qubits, it's about 3. The error percentage was able to be dropped by 1/3, and the performance technology and the manufacturing technology has improved as well.
Now you will see this for yourself later, but the quantum computer is currently stopped so that you can look inside. Last week it was operational, and so let me show you the video from that. So today it's a bit more cosmetically beautiful, but this is during the experiment. So this is the refrigerator. The bottom is a bit bigger than the 64 qubit version. And on the right hand side, you have the power, the DC power. And then on the left hand side, you have the control where the microwave is being emitted. And then there's a huge set of cables, which is used to control the qubit. So everything is hidden today. It's covered today, but in actuality, it's like this. So the noise is a bit down, turned down for now, but actually it's very, very loud. And so you'll be able to see this yourself today. So from the time of 64 qubit, we don't want to just provide the quantum computer. We want to provide it as part of the hybrid quantum platform. So we have the 64 qubit computer, and then the 256 qubit superconducting computer is connected to that, to the 64 and the 40 qubit simulator. And so this will be provided as part of a platform to the customers. And we want to scale up and we want to expand the performance through a range of software technologies that are under development. So to give you just one example, one qubit chip to be able to be used by multiple users together. So because of the large performance of the qubits, multiple users will be able to use the same chip. And regarding the classical quantum computer plus the quantum computer, you need a hybrid job. So the high-speed hybrid job performance, that kind of technology is being developed as well. So for the 2056 or the 1000 qubits, one reason that we are developing this is to do the fault-tolerant quantum computing test. for the error correction. Because if there's a lot of errors, no matter how big the qubit is, it's not going to give a good performance because the higher the qubit, the error impact will be larger. So error correction is a must. So that is why we're doing the experiments for error correction. The other day, Google released a very wonderful paper regarding the code distance 7 error test. For the 2056 qubit, you can do the code distance 7. That's quite possible. And by changing the layout, you can also go as far as the code distance 11, which has not yet been experimented before. But this is why what we would like to do with the 256 qubits, and with the 1000 qubit, we can do an even larger code distance. So I talked briefly about the 1000 qubit system. Mahajan already talked about this as well. We are constructing a facility for the 1000 qubit system at the Kawasaki Technology Park. And this will be available from October. And we will start the development of 1000 qubit system once the facility is ready in October. So future outlook. March 31st, the 2056 qubit system is operational, but we're also doing various tuning and experiments. And by the end of the first quarter, we will provide a 2056 qubit system as part of our platform to the customers. And we will continue to work on the various applications, and we will conduct error correction experiments. And the 1000 qubit system development and beyond, we will continue to work on that as well. And this concludes my presentation. Thank you so much.